Hello. So, in this example, I'm going to walk through an actual, honest-to-God, real mathematician proof of a limit. So, depending on what class you might be watching this video in, if it's marked optional, which will likely be the case, then it's worth noting that what I'm about to do is not something that is, likely expected of you to do in your own class. This is just, if you're curious how it is that mathematicians actually rigorously prove these limit things instead of saying like, oh, it sort of makes sense, or, we're always using nice functions and things. This will be sort of a real honest-to-God example of what real mathematicians do when they have to do this kind of thing. It's worth a mention that this kind of thing, if you find it interesting and you want to pursue this level of math, this is what we do in the advanced calculus course. That's actually the name of the class. It's a 4,000 level class, MAA. In the math department, we offer it all the time. And so this is the kind of thing that we actually do in that class. We do this level of proof. It also requires that you've taken actual math proof and you understand structure of proof and these things. I'm going to try to present this in a way that sort of assumes that you haven't taken math proof. So although I'm going to write a real honest-to-God proof here, it'll be, like I said, I'm not going to pull any punches or anything. This is going to be a real thing, not watered down or sugar-coated or any of that. But nonetheless, I'm going to try to explain what's happening and like why this proof is written this way and how it's working. Okay? All right. So my question starts, all right, it says prove that this limit is this thing. So right off the bat, it's not asking me to find the limit. It's asking like, okay, I'm going to give you at least supposedly what the limit is. One of the things about proof is you never really sort of take it for granted. You always want to be like, is that true? Because maybe I have to disprove it, right? You claim to prove, but maybe it's not right. But in this case, it's pretty easy to see, right? So we look at this and it says, okay, prove that the limit as x goes to 2 of x squared plus 1 equals 5. X squared plus 1 is a nice continuous thing. I could just plug in 2. 2 squared is 4, plus 1 is 5. Of course, that works. And in fairness, actual math people would do that. They'd say, clearly this thing is continuous, so I can just plug in the value and get the number. But that's not the point of this video. The point of this video is to walk through an actual proof. So that's what I'm going to do. I'm going to start by declaring that that's what I'm going to do. So I'm going to say, okay, proof. All right, it's a little abbreviation. Now, as was sort of mentioned in the conceptual video part, we want to do this by using these little tiny error pieces that we call epsilon and delta. So the way we want to think about this is that it's sort of a conversation, like I'm claiming that this is what the limit is, and I have somebody who's very skeptical who disbelieves, right? And in order to show that this is what the limit is, right? I'm like, okay, the limit is x goes to 2 of x squared plus 1. I say it's 5. Another person says, I don't believe you. So my job then is to say, okay, for whatever level of accuracy you want, right? Because I don't know their context. They might be building a, galaxy simulator, and being within 1 might be fine because they don't have to be that accurate. Or it might be a particle accelerator, and I need like 10 to the minus 16th level of accuracy or some craziness, right? So I don't know what level of accuracy that person wants, so I need them to provide it to me. But obviously I don't have a person here to do that. So I say, okay, give me a level of accuracy. I'm going to call that thing epsilon. Whatever that person gives me, I'm saying, okay, I'm going to denote that epsilon, fill in whatever you want. So my first line is literally that part of the conversation. I say, okay, wish I had a marker that was waving around, getting dry, sorry. So let epsilon, this weird sort of E looking thing, greater than 0 be given. And so this really is, I'm saying, let it be given, let somebody give it to me, right? That person is giving me their context. And I'm making a note here that it's bigger than 0 because it's supposed to represent an error, right? It's supposed to represent how far away from the right value I'm allowed to be and still be considered close enough, right? Because that's how the limits work. I don't know what it is at the point, but I'm claiming that I get as close as you would want to whatever value I think the limit is. So this epsilon is sort of the furthest away from 5 I could possibly be and still be correct. Now, the only thing I have control over then is how close can I get to 2? Because effectively what I'm arguing is that if you're close enough to 2, then whatever value you pick, that's my sort of definition of close enough to 2, will be your definition of close enough to 5. So on the one hand, I have epsilon, your definition of close enough. Now I get to introduce my idea of close enough. And I'm going to think of that as delta, okay? So I'm going to choose delta, this weird curvy d, greater than 0, such that delta equals something. Now, it's worth a mention here, actually it's a key idea here, that delta is how I'm getting close enough to 2 in order for me to be sort of the result after I do something squared plus 1 to be whatever that person thinks of as close enough to 5. So inherently delta has to depend on epsilon, because as epsilon changes size, I could be further away or have to be closer to 2 in order to match that level of accuracy. So what I'm about to write here needs to do something with epsilon. Now, this is where the proof gets weird. I know you're probably thinking, you're like, already kind of weird, but bear with me because it's about to be like rabbit out of a hat moment. Because what I'm going to write here is I'm going to say, okay, let delta equal, and in fact, really a nicer way of writing this, I can write equal, but for reasons that will be clear, I'm going to write less than. So I'm going to choose delta so that it's still positive, but it's less than the minimum of 1 and epsilon over 3. Okay. Now, if you're wondering to yourself, where in the name of all that is holy did that come from? Good, because you should be. This is the magic out of a hat, magic rabbit out of a hat, excuse me, moment in the proof. And the answer of where this comes from is actually because what happens without me writing it in the proof is that over here, I'm going to do a bunch of scratch work to figure out what delta I needed to choose. As it happens, I already know what that delta is, that's why I could write it, but I'm going to show you where this comes from, where we managed to think of this. So remember what delta represents. Delta represents the furthest distance I can be away from 2 and still hit my target. Meaning that if I pick an x value, I want the distance, the only thing I have control over is the distance from x to 2. So remember this is the distance bit, right? Absolute value of a minus b is the distance from a to b. So this is telling me that the distance from x to 2 has to be less than delta. That's the only thing I can control, is I can change this number to make this distance smaller or bigger, right? Right now, I don't know what delta is. Like, I pretend I haven't written this minimum piece here. I'm trying to figure that out. So I'm over here going, okay, I have control over that. What do I want? Well, what I want is for when I plug in an x value, right, and I have that x squared plus 1, I want the distance from that, whatever it actually is, the distance from that to 5, to be less than the epsilon I was given. So what I want is that the distance, again, absolute value, of x squared plus 1 and 5, x squared plus 1 minus 5, is less than epsilon. So how do I bring these two things together? This is where the magic happens, right? This is where you have to be kind of clever, because what I want to do is manipulate this thing to hopefully make this thing appear. The way I'm going to do that is I'm going to take x squared plus 1 minus 5 and sort of combine, simplify, factor, do whatever I need to do to make this x minus 2 appear. So in particular, if I put these things together, I get x squared plus 1 minus 5 is minus 4, which is x plus 2 times x minus 2. And I can use that the absolute value of the product is the product of the absolute values, meaning I can write this as x plus 2 and x minus 2. Now on the one hand, I have made this thing appear. Aha! This thing I know is less than delta, i.e. I have control. So what I mean by that is that I can force x minus 2 to be really, really small by making delta small, because the smaller I make delta, the smaller that difference is. But I still have this x plus 2 thing happening. But remember what this, what these mean. If my x distance, right, my distance from 2, x has to be pretty close to 2, right? In fact, I think I might have, this is what happens when I do off the top of my head. I think I actually want epsilon over 4, but this is why we're doing this. We'll find out what I need. So x has to be pretty close to 2 in order for this to work. And in fact, I sort of know that x can't be too far away from 2, because if I make delta some number, so let's say delta was 1, right? If delta is 1, that means that x can only be at most 3, because if we're bigger than 3, then when I subtract 2, I'd get something bigger than 1. So what I'm going to do here, I say 4, maybe it's 5. Again, this is what we're doing. So here, I'm going to suppose delta is, let's say, less than 1. So if delta is less than 1, then x has to be, so in particular, I can do this sort of more fully. Let me do it completely here. So if I were to do this as like the piecewise definition, I'd know that sort of if the biggest distance from 2 that x can be is 1, then it would either be 1, right, if I were 1 below, or 3 if I were 1 above. So in particular, x would then have to be between 1 and 3. So in particular, x plus 2 is less than the biggest x value. So if I plug in a 3, this would be less than 5. So this tells me that if I make sure delta is less than 1, then that tells me that x plus 2 is less than 5, which means this thing, thus running out of room, but I want to make sure to have it sort of tucked away here. Thus, x plus 2, x minus 2 is less than 5, because that's what x plus 2 is, times x minus 2. But remember, x minus 2 is less than delta, so this is less than delta. So in particular, it's a 5 that I want. If I make sure that delta is less than epsilon over 5, then that would tell me, right, if delta is less than epsilon over 5, then I could replace delta by epsilon over 5, and I would have just, right, this would be less than 5 times epsilon over 5, which is just epsilon. So this is the sort of argument that I'm after. So coming back over here then, I did indeed use the wrong number. I want this to be 5. But coming back over here, this is how I get delta. I say, okay, delta is less than. On the one hand, I came up with this epsilon over 5 for delta. So that's where this epsilon over 5 is coming from to make this computation work. But to get this far, I also needed delta less than 1. So I also need to know that delta is less than 1. And the problem is that if I'm thinking of epsilon as a small thing, right? If epsilon is 1/10, then I'm going to get 1/10 over 5 is 1/50th, way smaller than 1. That's why I sort of knew this would be reasonable. So, like, almost certainly this 1 isn't really important, but you never know. Some jerk might come along and be like, I'm going to choose epsilon to be 500. Ha ha ha. Now your epsilon over 5 is 100, not 1, and all of this argument blew up. Doesn't work, and now the whole proof is bad, right? So I sort of have to put a cap on delta to be like, yeah, sure, maybe you're going to give me some absurd epsilon that makes no sense in the context of this problem just to make my proof look bad, right? So that's basically why that 1 is there. Realistically, what I really want, and what will almost certainly be the case, is that it's this epsilon over 5, because epsilon is going to be something small. Having it bigger than 5, which is what I need before that 1 matters, if I'm saying the limit is 5 and you're like, but can you get within 5 of that? Like, that's ridiculous. So, all right. So I've now gotten delta, and the question is, okay, how does the proof work, right? So it's on me to prove without a shadow of a doubt that with the delta that I have defined, that I'm going to get within their argument, like their idea of close enough, whatever their context is, I'm going to get within that epsilon of what I claim the limit is, 5. And the way I'm going to do that is basically rewrite what I just did, right? So what I'm going to do is observe exactly that process. So I'm going to say, okay, you gave me an epsilon, I give you a delta, now I'm going to show you that I'm right. So in order to do that, I want to look at how far away is the thing. The claim, so again, to remind you, the delta is how far away the input can be. So I'm going to go ahead and fix one of these things as an input. I'm going to say, okay, fix x naught such that the distance from x naught to 2 is less than delta. So what I'm saying is, okay, if you're within delta of the target of 2, you're going to get within epsilon of 5. So to show you, go ahead and pick something that is within a delta distance, right? Whose distance from 2, absolute value, is less than delta. Now I'm going to show you that when you put that thing through the function, you put that thing through x squared plus 1, you're going to get within epsilon of 5. So I'm going to say observe, as in watch me prove to you that I am right. And yes, we really do write these things in proofs, like observe and whatnot. I'm going to say observe. And I'm going to do basically what I did over there. I'm going to say, okay, I'm going to look at the distance from x naught squared plus 1, that thing. So I'm plugging in x naught as my x up here, right? The thing that I have chosen that is close, my idea of close enough. And I want its distance from 5. And just like over there, I'm going to simplify. So this is x naught squared minus 4. Then I'm going to factor to get x naught minus 2 and times x naught plus 2. And I'm basically going to make this same argument. I'm going to say since x naught minus 2 is less than delta, I know that, and I'm just going to write this for the sake of space, I know that delta is less than 1 or something even smaller than 1. So in particular, it's definitely less than 1. That tells me, just like I did over there, that since the distance between these two things is less than 1, that tells me that 1 is less than x naught is less than 3. So, in particular, the x naught plus 2, just like I did over there, is less than 3 plus 2, which is just 5. Moreover, x naught minus 2 is also less than delta. Because, right, I have an x naught minus 2 here, but remember that's literally how I defined, like that's literally what I was doing with delta, right? Thus, I'm saying, given that information, right, I have now that x squared, x naught squared, excuse me, plus 1 minus 5, that thing I started with, is equal to x naught plus 2 times x naught minus 2, which is less than x naught plus 2 is less than 5, and x naught minus 2 is less than delta. But again, remember that delta is less than epsilon over 5, or something smaller than that, although 1 is almost certainly not smaller than that, but it is the minimum, so, you know, epsilon over 5 is definitely at least that. So this tells me that this is less than 5 times epsilon over 5, but that is just epsilon. And so I can see then, right, that I've started with the distance from the thing that I chose, whatever it is that is within my idea of closeness. The distance between that thing after I put it through that x squared plus 1 function and my target, 5, has to be less than epsilon, your idea of close enough. For any x naught, for any value of x that you choose, that is my idea of close enough to 2. So this works for every x that is within delta of 2, for the delta that I've defined, which again has to sort of depend on your idea of epsilon, because as you change epsilon, I have to make delta more or less strict to match that. So I'm done. And the way we show we are done, write a little square. I genuinely don't know where that comes from, but I'm sure it has a fascinating typographical background. I hope it's just not that, like, squares are cool. But you never know with math people. So that's everything. This is an actual legitimate mathematical proof that this works. Now, as we said at the beginning, you might be wondering, like, okay, but this is a really sort of obvious example, right? X squared plus 1 is continuous, so why bother, right? We could just plug it in. And as I said earlier as well, that's what an actual mathematician would do. They'd cite the continuity and just conclude that this thing is clearly 5. But this process is actually really important, because this is the same exact process that you would use for any kind of limit that you want to do of a function. And in fact, it always breaks down to let epsilon greater than 0 be given. Like when we teach this in advanced calc, we're like, this is always your first line. This is always the first line. It's that thing. And then typically the second line is almost always choose a delta with some property that turns out to be the right one, right? Turns out to be the close enough factor. And the way you find that is you do some clever manipulation in order to get something you have control over, something maybe you need to bound or do some other cleverness with. But generally speaking, it comes down to being clever enough to show algebraically that you can use your delta to make epsilon at the end. And historically, there have been lots of limiting type problems, even as recently as the early 1800s, which, like, yeah, it's a couple hundred years ago, but in math terms, right, like Pythagorean theorem is thousands of years old. So, like, generally speaking, that's pretty recent for math. And even then, as recent as the early 1800s, there were problems that required limits that people would make very intuitive, very convincing arguments as to what that limit should equal. And everybody accepted them. Very famous mathematicians, like really big minds of their generation, would make these arguments, and they were totally wrong. Like, they were completely incorrect as to what that limit should have been. But because they were so convincing and they were, considered intellectual giants, people just believed them because they didn't have an objective way like this to prove it. And so this is why this is what the push forward that Newton and Leibniz did. They found a way to do this with this epsilon-delta argument that was truly objective. As I said, it took a little while to be accepted everywhere, hence the, as recent as the 1800s, or found a way to apply it everywhere. But nonetheless, this gives a framework where you can write a proof that is either right or wrong, and there's no convincing needed. There's no intuition needed. It is cut and dry. You go through and you either end up with an epsilon or you don't. And this is all just algebra, right? You can check step by step to make sure my algebra is right, and that's how you get there. And so this gave a level of objectivity and rigor that was desperately needed, which is, why the Newton-Leibniz are considered sort of the fathers or the creators of calculus, as we call it, is not because they, created integrals and derivatives and things, although they effectively did in some sense, and not because they came up with a limiting process for the first time. As mentioned in another video, the Greeks had that as the method of exhaustion. That's been around for a very long time. The idea of iterating something sort of indefinitely. But they gave a framework under which this thing could be sort of done objectively and mathematically rather than intuitively and sort of argued over. Okay. So that is that. This is a epsilon-delta proof of a limit. Okay.